Hello, and welcome to this episode of Beginning Engineers. Today I'm going to be talking about statics and dynamics, staying still and moving. We will start off by asking, what is statics? Statics is a branch of mechanics concerned with the analysis of loads on an object that does not experience acceleration, so things that don't move. And I think sometimes we have a tendency to forget that just because something isn't moving doesn't mean forces aren't applied. Think about buildings or bridges. They don't generally move, yet there are all sorts of forces being applied to them. The equation for this goes back to one of Newton's laws. Force equals mass times acceleration. Now, if an object isn't moving, the acceleration will be zero. Now, in order for the equation to work, and we know that the equation does work, force must also be zero. And if that's the case, how can there be any force on the object at all? That doesn't make any sense. Doesn't zero force mean that there's no force? Well, no, not at all actually. In that equation, force means the summation of forces, that all forces equal zero. So for every force, there's an equal and opposite force, and that's Newton's third law. So this means that the sum of forces, or if you're talking rotation, summation of moments, must be zero. And this fact really allows us to solve for a lot of missing values. For example, in the image I have there, this would be a typical image you might see in a physics textbook. So if you've taken a physics class, you might have this as a problem. They would give you something like maybe the weight of the object, the friction coefficient, the angle of the plane it's on, but they would leave a few forces blank. But you could solve for these forces because you would know that the sum of all forces must equal zero. And you would know that because in the book it would say something like the object's not moving, it's just resting on the hill. So when it comes down to analyzing forces, there's a few ways to look at it. Forces, first of all, are vector quantities. So you have things such as mass and temperature that have no direction. They are scalar quantities. You wouldn't say it's 60 degrees up outside, or that you weigh 80 kilograms to the left. That doesn't make any sense. So quantities like that are scalar in nature. They don't have direction. But for those quantities that do have direction, they are known as vectors. They can be positive, negative, up, down, left, right. Opposites cancel out, and that ties into how force can be zero. Vectors can be symbolized with a few symbols: a large bold V, a lowercase underline v, or a v with an arrow on top of it. Mathematically, and in the real world looking at physics, you can also take two vectors and add them together and consider them one vector, which I think is very interesting. So look at the image in the top right. It's got an A vector going one way and then a B vector going another way. If you assume both those forces are on the same object at the same time, instead of thinking about them as two separate forces, you can just think about them like one vector that has the force and direction of the A plus B line. So A and B together really would do the same thing as the A plus B line. When you look at objects that are stationary, it all has to come back to zero. So look at the more complicated image on the bottom. You've got all these lines, all these vectors in different directions and different forces. But we assume this is a static system, so we know two things are true. The sum of all forces is zero. The sum of all moments, so the sum of all rotation, is also zero. Looking at the image on the bottom left, that adds up all the vectors, so the 1, 3, 7, 2, 5, 6, and 4 lines, they all take you back to your origin point. So those all add up to be a net zero force. That might just sound too good to be true, but if an object is at rest, if it's not moving, that is always the case. Otherwise, if one force won out, one direction of force was winning, it would be moving in that direction. The same thing goes with moments as well. So there's a central point, a pivot point, around which everything is forcing the object to rotate one way or another. You have the 2, 5, and 6 on top, and the 1, 3, and 4 on bottom. And you can see how the rotation is different in each of those images. But the power of the rotation for each one, the force of it, is the exact same. So the two rotations again cancel each other out. So those are the basic ideas behind statics, when things aren't moving. So what is dynamics? Dynamics is concerned with the motion of bodies, the forces applied to those bodies, otherwise if there's no force they wouldn't move, and the properties of the bodies themselves, so the mass of the body, the moment of inertia. It all goes back to that equation we were talking about earlier, force equals mass times acceleration. So dynamics really deals with inertia, which is the mass times acceleration, it's the force, the resistance to motion, how much force you need to really get something moving. It deals a lot with accelerations, represented by A. Dynamics deals with momentum, which is mass times velocity. So think about a big semi-truck moving at 20 miles per hour. It has a lot of mass and a pretty decent speed. It has a lot of momentum. If you have something that only weighs half as much, it has to go a lot faster to have the same momentum. And momentum is something I think is intuitive to a lot of us in the real world. Let's imagine a car crash. If you have a big semi and it's going to hit a little sedan head on, for the semi to not completely win and push the sedan the other way, imagine how much faster the sedan would have to go. An insane amount to have the same momentum. Dynamics also deals with reaction forces, so Newton's second law, which basically states that force equals mass times acceleration. So if you put force on an object with mass, it's going to accelerate. The diagrams for dynamic systems were similar to those we looked at for static systems. The big difference, of course, being that in dynamic systems, things are moving. So it's a lot of velocity and acceleration calculations. A lot of trying to understand if something falls or moves, where it is going to end up and how quickly, with how much energy. I think it's important to make a note of what is acceleration really. So I'm going to go briefly into a calculus concept, but keep it very simple. So if you've never had calculus, that's okay. Acceleration is the change in velocity over time. That's something we're familiar with. As you speed up, your velocity is increasing over time. But what's interesting about acceleration is it will always be the derivative of velocity over time. So look on that image I have there, that curve. It shows velocity increasing, then it decreases a little bit, then it increases again from left to right. So this is someone increasing their speed for a little while, a little bit of time, slowing down a little bit, and then increasing again. Now the way that derivatives work in calculus with graphs like this is that to find out the derivative of an equation at any point, you take that singular point and you draw a straight line that would only touch that one point on the graph. You can see in that image they chose a point on the concave bottom portion, so when whatever the object is slowing down. That derivative line would be the exact acceleration of that object at that exact point in time. And when I say that, I mean the slope of the straight line, the line that is tangent, that would only touch one single point on the graph. You could draw 1,000 different tangent lines for 1,000 different points on this graph, and you would get 1,000 different accelerations based on whatever point in time the line was at. And it's always the slope of the tangent line. Why it is important to know statics and dynamics? Well, statics and dynamics form the base for many other interesting fields of study. Fluid dynamics, which is part of aerodynamics, aeronautics, and hydraulics. So a lot of really advanced scientific and technological fields have a basis in statics and dynamics. It's important to know how physical objects interact and how forces are applied and what those forces do. That really helps progress technology. Also, a basic understanding of statics and dynamics will give an understanding to things like car crashes, explosions, gunshots, and many more items. You see a lot of funny videos on YouTube where they talk about how explosions would actually affect people in real life. A lot of times what you see in movies would kill people. They wouldn't be able to get back up, brush themselves off, and run and save the day. It's also dramatized the other way. When someone gets shot, in the movies a lot of times they get blown back. But in real life, understanding momentum, you would realize that bullet barely puts any momentum on a huge person. Same thing with a semi running into a bouncy ball. The bouncy ball is not going to affect the semi, just like the bullet is not going to push you back. Understanding Newton's 3 fundamental laws of motion really help understand statics and dynamics. If you can understand some basics about triangles and how to do some of the trigonometric math with it, you can understand a lot of statics and dynamics. you can understand a lot of the world in a scientific and mathematical way, and I believe that is very valuable. So I hope you enjoyed this overview of statics and dynamics. Thank you so much for watching this Beginning Engineers video. If you like it, please subscribe. I'll be doing many more engineering concepts in the future. Have a great day.